Hi everyone. In Chapter 2, we're going to begin by talking about the real number system as well as mathematical models, starting with section 2.1, which is about the natural numbers. When we mention the phrase natural numbers, this is also sometimes referred to as the counting numbers. It's the collection of positive whole numbers 1, 2, 3, 4, 5. So if you were to think about if you had like a group of items, and if somebody asked the question, how many of something do you have? We always begin our count with the number 1. So 1, 2, 3, 4, 5. This set is the set of natural numbers. It goes on forever. There are infinitely many of them, and they just continue to grow in size by 1. The next thing we're going to talk about is kind of some ideas related to multiplication, and that is the idea of a factor. A factor is a number that divides another number. So for example, if I look at the number 12, both 3 and 4 would be factors of 12 because they multiply to give the number 12. So if there's a value, for example, some other factors of 12 would be the numbers 2 and 6. So if I take, see if I can get my cursor up here. So sticking with the number 12, for example, we can write 12 as 2 times 6. So we would say that 2 and 6 are also going to be factors of 12. So natural numbers that multiply to get the product are called factors of the product. Let's see if we can find all of the factors of 24. Okay. So for the factors of 24, the easiest way to start is to try to go in order, starting with the number 1. We know that 1 times the number itself, 24, gives us 24. So 1 is going to be a factor of 24, as 2 is 24. If we go in order, so after 1, the next natural number would be 2. And sure enough, 2 does go into 24 12 times. 2 times 12 gives us 24. So both the number 2 and the number 12 work. 3 also goes into 24. 3 goes in 8 times. So 3 and 8 are going to be factors. 4 goes into 24 6 times. So 4 times 6. So both 4 and 6 are factors of 24. Now 5 will not go into 24. So 5 is not a factor of 24 because there is not a natural number that you can multiply by 5 to get 24. Now 6 does go into 24. We know that 6 goes in 4 times, but we've already written both of these factors when we did 4 times 6. And any other factors that kind of come from continuing this pattern would just be the reverse order of the factors that we already have. So if we list them kind of in order, it turns out that the factors of 24 are going to be 1, 2, 3, 4, 6, 8, 12, and 24. Part B says, can you think of a number that has only 2 factors? One example would be the number 2. The only factors of 2 would be 1 and 2. 3 is another example, as is 5. And in general, this is the definition of a prime number. A number is prime if it only has 2 factors, and those factors will always be the factor 1 and the number itself. Can you think of a way to write 24 as a product of more than 2 natural numbers without using the number 1? There are many different ways we can do this. For example, I know I can do a 2 times a 2 to get 4, and then from there we would need to do 4 times 6. So we could write 24 as 2 times 2 times 6, and this is writing 24 with 3 factors. Another way we could have done this is I could have done 2 times 3 times 4. That should also work. This is 2 times 3 is 6, and then 6 times 4 will give us 24. That's yet another way to write 24 using 3 factors. And we could even do it with a little bit more. I can write 24 as 2 times 2 times 2 times 3. And this is writing 24 as the product of, now we have 4 factors. We say that a natural number a is divisible by another natural number b if dividing a by b results in a 0 remainder. So when we talk about divisibility, and in particular we mean that it divides evenly, we say that there's 0 remainder. So for example, we know that 6 is divisible by 3. Precisely because when we take 3 into 6, it goes in evenly 2 times, and it would leave a 0 remainder. So 6 is divisible by 3. However, 6 would not be divisible by 4, because 4 will not go into 6 evenly. If we take 4 into 6, it goes in once, and notice, and then you would have a remainder of 2. So when number divides another number with 0 remainder, we say that it's divisible by that number. We've already come to the notion of prime. We said that a number is prime if it has exactly 2 factors, namely the numbers 1 and itself. A number that is not prime, i.e. a number that has more than 2 factors, is called a composite number. The natural numbers can be broken into these 2 categories. Every natural number is either a prime number or it is a composite number. For example, let's try to decide whether each of the following numbers is going to be prime or composite. 25 is going to be composite simply because it has more than 2 factors. The factors of 25 would be 1, 5, and also 25, because you can write 25 as 5 times 5. So 25 is going to be composite. For 17, its only factors are 1 and 17. So 17 is going to be prime. 12, we've seen from an earlier work, we know that 12 is going to be composite. It has a lot of factors, more than just 2, namely 1, 2, 3, 4, 6, 12, for example. And now we get to 31. 31 is going to be a prime number as well. The only factors of 31 are going to be 31 in itself. So 2 very important definitions, the definition of prime and composite. In many ways, kind of like if you look at like chemistry, how the atoms are like the building blocks of molecules, the prime numbers are really kind of like the building blocks of the natural numbers. And that this is kind of follows from what's called the prime factorization theorem, also called the fundamental theorem of arithmetic. And this states that every every composite number can be written as the product of prime numbers in exactly one way. And when we say exactly one way, this means up to ordering of the primes. So for example, a little bit earlier, I wrote 24 as a product of 2 times 2 times 2 times 3. We're going to refer to this as the prime factorization of 24. There were other multiplications of 24. Like, for example, we also saw that 24, one way that we were able to write it was as 2 times 3 times 4. Okay. However, 2 times 3 times 4 would not be a prime factorization here. Because if we look at it, this number 4 is not a prime number. Right? So when we talk about the prime factorization of a number, every single factor in that product should be a prime number. 2s and 3s are both primes. Furthermore, when we say exactly one way, this would not be counted a different way. If I just kind of reorder it and write it as 2 times 3 times 2 times 2, well, that also gives 24, but it's really no different than the prime factorization I have above. It has to contain 3 2s, and it has to contain 1 3, and the order doesn't really matter there. Typically, whenever we do our prime factorizations, we will always order our primes, though, from least to greatest. Okay. The easiest way to find a prime factorization is with the use of what's called a factor tree. So if I want to find the prime factorization of 100, which is we want to write 100 as the multiplication of using only prime numbers. The easiest way to do this is I'm going to start off by taking 100 and dividing it by 2, because I know 100 is divisible by 2. 2 goes into 100 50 times. And so I have this kind of 100, which is now split into two factors. 2 times 50 gives me 100. Notice that this number 2 is a prime number. It will not break down anymore, so I'm going to circle it. So that branch of my tree is done. The 50, though, I can take 2 into that again. 2 will go into it 25 times. Again, 2 is prime, so that branch will not break down anymore. I'm going to circle it. And then we can write 25 as the product of 5 and 5, where both of those are prime. So I'm going to go ahead and I'm going to circle those. I see that my branches are now totally done. Every branch has ended. And what we have left is we have 2 2s and 2 5s. So we can write 100 as 2 times 2 times 5 times 5. And if you want to, you can check this. 2 times 2 is 4. 4 times 5 is 20. And then 20 times 5 does give us 100. And notice that every single number that's here is a prime number. Because of the fundamental theorem of arithmetic, we know that this factorization is unique. So we have successfully found the prime factorization of 100. We can write this, and we're going to focus on this in the coming sections, but a more convenient way to write this would be using what's called exponential notation. Notice that we have 2 2s and we have 2 5s. So in a little bit, we're going to write this as 2 squared times 5 squared. In my opinion, this is the best way to do the prime factorization tree, is to always work with divisors that are primes. So start with the first prime of 2. And then once 2 will no longer go into the numbers, try the next prime, which would be 3, 5, 7, etc. Some people will try a slightly different approach, which also works, and that's just to try to find any way at all that you can find two numbers that multiply to give 100. For example, some of us might look at this and say, oh, I think of this as 4 and 25. You can split it apart that way as well, but just notice that this first branch will break down even more. 4 is 2 times 2. So we circle it, that one's done. And the 25 is 5 and 5. Okay. Slightly different approach. Instead of focusing on primes, we just look for any factors that work. But notice at the end of the day, we get exactly the same answer. This shows a prime factorization of 2, 2, 5, and 5. Let's see if we can find the prime factorization of 360. I'm going to begin by kind of focusing on primes. The first prime is 2, and I know 2 can go into this number. 2 will go into it 180. The 2 is prime, so I'm going to circle it. 2 can go into 180 90 times. So 2 is done, I circle it. Now 2 will go into 90. 2 goes into 90 45 times. Circle it. 2 will no longer go into 45. The next prime, which is 3, will though. And I know that 3 is going to go into there 15 times. 3 is prime, so I can circle it. And then lastly, 3 will go into 15 again. 3 goes in 5 times. It's prime. And the 5 is also prime, so we would be finished. To write our final answer, it should be a factorization, so I need to write a multiplication. We have 3 2s, so 2 times 2 times 2. We have 2 3s. And we have 1 5. Again, if you look at this list, all of these numbers are primes, and their product multiplies out to exactly 360. When we start to discuss exponents, we'll see that a shorthand way we can write this is we have 3 2s, so that's 2 to the third. We have 2 3s, so that's 3 to the second. And then we just have our 1 5. So this would be the prime factorization of 360. There is another approach that some people like to use, which is called the division method, which is also sometimes referred to as a division ladder. And whenever you're doing this method, you have to focus solely on primes. For example, I can take 2, which is the smallest prime, into 140. We know that goes in evenly, and it goes in 70 times. And then what you do is you continue to divide by that quotient. So that's why they kind of call it a division method or the ladder method. I know that 2 can go into 70, and that's going to go in evenly 35 times. 2 will not go into 35. The next prime, which is 3, will not go into 35. But the prime after that will is going to be the number 5. 5 goes into 35 7 times. And then 7 is a prime which goes into itself once. So in the division, or sometimes called the ladder method, you keep dividing your answer until you get to the number 1. And then the prime factorization is simply the divisors that you had right up until you get to the number 1. That's 2, 2, 5, and 7. So 140 we can write as 2 times 2 times 5 times 7, or you can call it 2 squared times 5 times 7. This is an alternative approach to the factor tree method. I personally find that the majority of my students tend to like the factor tree method better, but this is just another approach that some people use, and if you like this division method or ladder method, you're certainly welcome to do it. Let me try it one more time. Let's try it with 240. So obviously the smallest prime is 2, which does go into 240. It goes in 120 times. 2 does go into 120. It goes in 60 times. 2 does go into 60. It goes in 30 times. 2 goes into 30. It goes in 15 times. 2 will not go into 15, but 3 does. It goes in 5 times. And then 5 goes into itself 1 time, which is a prime. So these are the numbers in front of our ladder. And we see that 240 is equal to, we have 1, 2, 3, 4 2s. We have 1, 3, and we have 1, 5. So 240 is going to be 4 2s, 1, 3, and 1, 5. And that would be our prime factorization. Again, if you want to, notice you'll get the exact same answer if you do the factor tree. 2 and 120, that's prime, so circle it. 2 and 60, circle the 2. 2 and 30, circle it. 2 and 15, circle it. And then we get our R3 and R5. So again, prime factorization has to be unique. No matter which way you do it, you should come up with 4 2s, 1 3, and 1 5. The next topic we're going to come to is that of the greatest common factor. When we have 2 or more numbers, as the name kind of implies, the greatest common factor, also abbreviated GCF, is a number that has to be a common factor, meaning it has to be a factor of all of the numbers that are involved. And not only that, but it has to be the largest of the common factors. So as an example, if I look at these numbers, okay, the number, let's say 24 and the number 18. We could find all of the factors of each of these numbers. For example, 18 would have factors of 1, 2, 3, 6, and 9. So those are all of the factors of 18. The factors of 24, we did that earlier. The factors of 24 we said was 1, 2, 3, 4, 6. Don't want to forget 8, 12, and then 24. So to be the greatest common factor, it has to be common. Notice that both 2 and 3 are common factors of both 18 and 24. But the largest factor that's common to both of them is this number 6. So we would say that the greatest common factor of 18 and 24 is 6. This process, which I just did for this example, works out kind of nicely because 18 and 24 are small numbers that don't have that many factors. But this would be a really difficult process to do if your numbers have a lot of factors or if they start to get large. There's an easier and much more efficient way to finding the GCF, which utilizes our prime factorization that we just talked about. In order to find the GCF of two or more numbers, the first thing we are going to do is we're going to write out the prime factorization of each number. Once we have the prime factorization, we're going to make a list. We're going to write it with exponents. We then go through for the prime factors with the exponents, and we choose the smallest power that appears in each. And then the GCF is just going to be the product of those numbers that we found in step 2. Let me give you an example of this. So we're going to start off with 72 and 180. So to begin, we need to do the prime factorization of each of these numbers. 72, I know that's 2 and 36. Circle this. 2 goes into 36, 18. Circle the 2. 2 goes into 18 9 times. And then 9 is 3 and 3. So the number 72, it's 2 times 2 times 2 times 3 times 3. So I have 3 2's and I have 2 3's. So that's my prime factorization for 72. 180 is going to be 2 times 90. Did we do this one already? Nope, didn't do 180 yet. So it's what? 2 and 90, 2 and 45, 3 and 15, and then 3 and 5. So for 180, its prime factorization, we have what? 2 2's. We have 2 3's. And we have 1 5. So let's go ahead now. We're going to use this information to find the GCF. And I'm going to put this in orange. So in order to find the GCF, here's how it's going to work. We go through our prime list, and we need to find the primes that are common to both lists. So I see 2's and 3's. So we're going to pick 2's and 3's. Notice that even though the 180 has a factor of 5, there is no 5 in the number 72. So because it's not common to both of them, it's not going to be part of our GCF. We now go ahead and we choose the smallest power of each prime that appears in any one of the numbers. So if I'm looking at the factor of 2, which one had the fewest amount of 2's? Well, the 180 had 2 2's, the 72 had 3, so the smallest number is going to be the 2 2's, which means that there's going to be 2 2's in our GCF. If we look for which one had the fewest amount of 3's, it's actually a tie. Both of them have 2 3's, so there'll be 2 3's in the GCF. And you can think of this in the same way with the factor of 5. The 72, which doesn't have any 5's in it, you can think of kind of generically as having 5 to the 0 power. We'll talk about this, but anything to the 0 power is just 1. So you wouldn't ever really write this as a part of it, but you can think of that as having 0 5's. And then the question becomes, well, which one had the fewest 5's? The 180 has 1 5, the 72 has no 5's, and obviously 0 is the smaller amount, and that's where we're not going to have any or 0 5's in the GCF altogether. So this process actually gives us the GCF of the two numbers, but it gives it to us in factored form. We can multiply it out to see what the number is going to be. We know 2 squared, 2 times 2 is 4, 3 squared is 9, and then 4 times 9 is 36. And again, what that 36 represents, 36 evenly divides 72, and it divides 180. So the 36 is a common factor. Not only that, but it's the largest factor that divides into both of those numbers. So to find the GCF, this is the process. You take your numbers, you write out the prime factorization of each, you then look at all of the different primes that appear, and you choose the smallest power of each prime that's common to both lists. Let's take a look at another example. So we want to find the GCF of 40, 60, and 100. This would begin by doing the factor tree of each, which I'm going to skip for this part. But if you do the prime factorization of 40, you should get 2 times 2 times 2 times 5. So that's going to be 2 cubed times 5. If we do the prime factorization of 60, that should be 2 squared times 3 times 5. And if you do the prime factorization of 100, that's going to be 2 squared times 5 squared. Again, you would work these out, do the factor tree for each. This is what we should come up with. In order to find our GCF, we're now going to go through and look at our list. And we want to see what are the different primes that show up. I see 2s, 3s, and 5s. So I'm just going to put for right now 2s, 3s, and 5s in it. Which one had the fewest amount of 2s? Well, it's kind of a tie between these two numbers here. The 60 and 100 each had 2 2s. So my GCF is going to have 2 2s. If we look for the factor 3, notice the 3 isn't even common at all. The 40 and the 100 don't have a 3 in it. So the GCF isn't going to have a 3. So you can think of that as a 0, or you could have just began the list by not even including the 3. The only primes that are common to all three lists are the 2s and the 5s. Furthermore, which one had the fewest amount of 5s? Well, that's kind of a tie between the 40 and the 60. Each one of them had 1 5, so the GCF is going to have 1 5 in it. So our final answer, what is the GCF of 40, 60, and 100? It's 2 squared times 5 to the first. That's 2 times 2 times 5, which is the number 20. 20 is the largest factor that will evenly divide all three of 20, excuse me, all three of 40, 60, and 100. Let's take a look at an applied example of this kind of thing. Suppose we have a worker that wants to package 200 packets of decaf and 280 packets of regular coffee. The plan is to package them for sale so that there's only one type of coffee in each box, and every box has to have the same number of packets. How can this be done so that each box contains the largest number of packets possible? So kind of going back to our chapter 1 material, we have this problem here. So we want to read it through and we want to kind of understand the situation. Our goal is we want to find one box size that we can evenly split up our decaf in and our regular coffee in. So both boxes, the box type we're going to use has to be able to fit them all equally. So let's think about this for a minute. So whatever our box size is going to be, it's going to have to be a number that can evenly divide 200, and it has to be a number that's going to evenly divide 280, which means that the size of our box has to be a factor of both of these. And because we want to fit the largest number of packets possible into each box, that means it has to be the greatest common factor of both of these numbers. So the way the problem is set up, the answer that we're looking for is actually going to end up being the GCF of 200 and 280. So let's go ahead and find that. We know how to do that from before. It's going to begin by doing the prime factorization for each. 200 is 2 and 100. Circle this. This is going to be 2 and 50. Circle that. 2 and 25. 2 is prime. And then 25 is 5 and 5. So the factors of 200, we have 3 2s and we have 2 5s. Let's take a look at 280. What are the factors of 280? That's going to be 2 and 140. It's going to be 2 and 70. We can do 2 and 35. And then 35 is going to be 5 and 7. So for the 280, we have 3 2s. We have 1 5. And we have 1 7. So we found the prime factorization for each. We are now going to go ahead and write out the GCF. So in order to find the GCF, we look at what are the primes that are common to both lists. Both lists contain 2's and 5's. So our GCF is going to have 2's and 5's. And then we go through and we choose the smallest power of each prime that is common. Which one had the smallest amount of 2's? Well, it's a tie. Both of them had 3 2's. So the GCF is going to have 3 2's. Which one had the least amount of 5's? Well, that's going to go to the 280. It had 1 5. So there will be 1 5 in our GCF. If we multiply this all the way out, this is going to be 2 times 2 times 2 times 5, which should give us 40. Again, this is a real-world problem, so we should be giving a real-world solution to this. The question says how many of each type can we put into the box? Well, we can put 40 packets of any one given type in a box. So the size of each box will be 40. Notice that if we do that, if we have 200 packets of decaf and we're breaking it apart into boxes of size 40, we will actually end up getting 5 boxes of decaf altogether. And if we take 40 into 280, that's going to go in 7 times, and we will have, 7 boxes of regular. So by doing that, by finding that GCF of 40, we're able to divide all of our coffee up into equal sized boxes. Each box is going to have 40, and it's the largest possible amount we can fit into each box by doing so. The next topic we're going to come to is the least common multiple. The least common multiple, or LCM, of 2 or more numbers is the smallest number that is a multiple of each. That is, the smallest number that is divisible by all of the numbers. For example, let's investigate the concept of the LCM using the numbers 18 and 24. If I start with the number 18, so I have 18, which would just be 118. If I have 2 18s, there we go. So 2 18s, that'd be 18 plus 18, that would give me 36. If I have 3 18s, that's going to be 54. If we have another 18, that would be 4 times 18. That would be, 72? And then if we have one more 18, that would bring us up to 90. So these are the first 5 multiples of 18. Next we come to 24. The first multiple of 24 is 24. 2 times 24 would be 48. 3 times 24 would be 72. 4 times 24 would be 96. And then 5 times 24 would be 120. So these are the first 5 multiples of each number. And when we say the least common multiple, it's the smallest number that is a multiple of each of them. And if we look through this list, that's going to be the number 72. 72 belongs to both lists, and it's the smallest such number. If we were to keep on going, there would be more numbers that are going to be common. For example, we stopped short, but you would have 144, and then over here in the list of 18, 144 would have been yet another common multiple. But in terms of being the least or the smallest common multiple, that goes to the value 72. So the LCM of 18 and 24 is going to be 72. Again, this method of trying to list things out becomes very inconvenient and extraordinarily time-wasting when the numbers get to be very, very large. Okay? there has to be a better way to do this. And again, we can find the LCM more easily by using the prime factorization of each. So let's do this again, but let's do so by finding the prime factorization of each first. 18, if you do your factor tree, you should get 2 times 3 squared. For 24, that's going to be 2 to the third times 3. In order to find the LCM, here's how it's going to work. For the LCM, we just take any prime that appears anywhere. So if a prime appears, even if it's just in one of the numbers, if you see a prime appear in any of the factorizations, then it's going to appear in the LCM. So the LCM is going to have both 2's and 3's in it. Unlike the GCF, when it comes to the LCM, you go through each list and you choose the highest power of each prime. So which one had the most 2's? Well, that's the 24. It had 3 2's. Therefore, the LCM is going to have 3 2's. Which one had the most 3's? Well, that was the 18. It had 2's, 3's. Therefore, the LCM is going to have 2 3's. And then if we just multiply this out, 2 cubed is 8, 3 squared is 9, and so we get the 72 that way. So just like when it came to finding the GCF, the prime factorization is going to be a very helpful tool in order to find the LCM. To find the LCM, we do the prime factorization first. We make a list of the primes that appear in any one of the factorizations. So if the prime appears anywhere, then it will appear in the LCM. And then you go through your list and you choose the highest power of each prime from the individual numbers. Let's take a look at example 11. We want to find the LCM of 24, 30, and 42. So I'm going to skip that work, but again, you would begin by doing the factor tree. 24 we know is 2 cubed times 3. 30 is 2 times 3 times 5. And then 42 is going to be 2 times 3 times 7. In order to find the LCM, we look at these lists and we write down what are the primes that appear. I see 2's, there's 3's, 5's, and then we also have some 7's as well. So the LCM is going to include 2's, 3's, 5's, and 7's. And now we go through list by list and choose the highest power of each prime. Which one had the most 2's? Well, that's the 24. It had 3 2's. Therefore, our LCM is going to have 3 2's. It's a tie. Each one of them had 1 3. So in particular, the most amount was 1 3 in each one. Notice that the 24 and the 42 didn't have any 5's. However, the 30 had 1 5. So 1 5 is the most. So we're going to have 1 5 in the LCM. And similarly, the only one that had a 7 was a 42. So it had the most with 1 7. So this gives us our LCM, but it's in factored form. It's going to be 2 cubed, which is 2 times 2 times 3 times 2 times 3 times 5 times 7. And if we multiply that all the way out, we should get 840. So the LCM of all of those numbers is going to be 340. It's going to be 840. Let's take a look at example 12. In example 12, they make the comment about noticing how hot dogs typically come in packages of 10, but most hot dog buns come in packages of 8. What's the smallest number of packages we can buy of each so that we end up with the same number of hot dogs and buns? So we need to have a number of dogs and a number of packages of buns so that we can have one bun for each hot dog. So notice that how many packs of hot dogs we buy If we have 1 pack of hot dogs, we have 10 hot dogs. If we have 2 packages of hot dogs, then we would have 20. So however many hot dogs we end up with in total, it's going to be a multiple of 10. Similarly, if we have 1 package of buns, we have 8. If we have 2 packages, we'd have 16. But the total number of buns that we're going to come up with is going to be a multiple of 8. In order to make sure that each hot dog has a bun, we have to make sure that the number of dogs and buns is going to be a common multiple of both 10 and 8. However, because they tell us that we want to buy the smallest amount, that means that we're going to need the least common or the smallest multiple of both of them. So in order to do this, let's find the LCM of 8 and 10. Again, this is going to begin by doing the prime factorization of each. You do your factor tree. 8 is 2 times 2 times 2. 10 is 2 times 5. To find the LCM, we write down any prime that appears anywhere in any of these lists. And we see that it's going to be 2s and 5s. So those are the only ones that appear. We now choose which one had the most amount of 2s. Well, the answer is it's going to be the 8. It had 3 2s, so it's going to have 3 2s. Which one had the most 5s? Hold on 1 second. Sorry about that. So which one had the most amount of 5s? That was the 10. It had 1 5. Therefore, our LCM is going to have 1 5. We have our LCM, but it's in factored form, so we can go ahead and multiply it out. We have 2 to the third, which is what? 8 times 5 for an LCM of 40. And I think this is probably one of those problems where most of you could probably have just looked at the 10 and the 8 and came up with the 40. But when the numbers aren't so nice or when they get large, you really want to make sure you're relying on this process of doing the prime factorization, identifying any prime that appears in any of our lists, and then we always choose the highest power of each prime for the LCM. Again, this is a real-world question, so we should be giving a real-world answer, and let's be very careful about what's being asked. So the LCM, the least common multiple, is going to be 40, which means that we're going to end up eventually with 40 hot dogs to pair with 40 buns. But the question didn't ask how many hot dogs and buns. It said how many packages of each should we buy. So we need to end up with 40 hot dogs. Notice that the hot dogs come in 10 to a pack. So the number of packages we're going to need to buy, 40 divided by 10, will give us 4 packs of hot dogs. And similarly, if we look for the buns come in packs of 8. So to get 40 buns, when they come in packs of 8, that means we're going to need 5 packs of buns. Okay. So again, a worded problem deserves a worded answer. So we need 4 packs of hot dogs and 5 packs of buns.